By the end of this video, you should be able to explain the water solubility of carboxylic acids, describe the reactions of carboxylic acids with metals, carbonates, and bases, describe esterification reactions, describe hydrolysis of esters, and state the uses of esters. Okay, so carboxylic acids, we've met these before very briefly at AS. Their functional group is C-double-bond-O-OH. So technically they are not a carbonyl, and because this OOH is actually kind of interconnected, works together, okay, so it's not a C-double-bond-O on its own. So when naming carboxylic acids, the carbon of the COOH is always carbon 1. Okay, so a bit like aldehydes in that carbon of the COH is number 1. Okay, so let's have a look at a few quick examples. Should be pretty straightforward. Propanoic acid, 3 carbons, nice and easy. This one, 3-methyl butanoic acid, and then let's go for a slightly trickier one. 1, 2, 3, 4, 5, 6. Okay. So Br and a Cl. So this will be 5-chloro. I'm going to run out of space, obviously. 4-bromo pentanoic acid. So it's not 1-chloro, 2-bromo, 5 or pentan 5-oic acid or something like that. It's pentanoic acid. This is carbon 1, and these are 4 and 5. Okay. So solubility. Carboxylic acids, very soluble, and this is because they contain polar C-double-bond-O and OH, which allow formation of hydrogen bonds. Okay, so then I'll just label up some dipoles there. So you know that delta minus and then delta plus. And, we've got some lone pairs as well we might add. Okay, so we get lots of hydrogen bonds. However, as chain length decreases, so as you go from, say, propanoic acid, or chain length increases, I should say, the chain length increases, so from propanoic to, say, dodecanoic acid with 12 carbons in the ring, in the chain, solubility decreases. Okay, so you've got more of all these carbons and hydrogens, not very soluble in water, and it overcomes the polarizing effect of the functional group. Okay, so reactions. Essentially, guys, carboxylic acid have the normal reactions in comparison with other acids. Okay, so we'll have a look at a couple, but these should all come as no surprise to you. They're all the standard reactions we expect at AS of acids. Okay, so we're going to start with, we'll do ethanoic acid because it's only got 2 carbons and it saves my space. If we react it with a metal, so we pick sodium, we're going to get this compound, and that is a salt. So acid plus metal goes to salt, and hydrogen, I'm going to put a half on the H2. You could do 2s, it's up to you. And this is ethanoic acid, and the salt we form is sodium ethanoate. So going back to our esters, when we are struggling to name them because of the acid and alcohol thing, getting them confused and all around, the reason why they're that way around is because the acid is the one that forms this ion, this anoate ion. Okay, so let's choose a different acid this time. We're going to go propanoic acid, and we're going to react it with KOH, potassium hydroxide. So we're going to try and choose some slightly different compounds, just so you're not thinking that ethanoic acid and sodium hydroxide are the only things we can have. So we get a salt and water. So this is propanoic acid, and this is potassium propanoate. Okay, so propanoate, and obviously water there. Okay, and the final one is our reaction with the carbonate. So let's do methanoic acid. Just think, yeah, that's balanced. Okay, so methanoic acid. Let's do it with sodium carbonate, Na2CO3. Obviously, CO3 is a 2- ion. Na is +1. Okay, so we get COO- and Na+. H, COO-. That should be H there as well. And carbon dioxide and water. And so the products there, so we've got methanoic acid to start with. Methanoic acid. And then we're making sodium methanoate. Okay, and we have to balance that quickly. So we've got 2 sodiums, so 2 there, and we need 2 here. Does that balance? One, 2, yeah. Yeah, so 2 for the water. Okay, so that balances there. So those are our standard acid reactions, just the same for carboxylic acids. Okay, so let's move on. So there should be nothing different there. Okay, and we're going to have a look at making esters. So let's start off with propanoic acid, and we've met at AS. Our general reaction for an ester is acid plus alcohol goes to ester plus water with an acid catalyst. And this here is ethyl propanoate. Okay, so ethyl is this bit here, and the propanoate is this bit here. I'm sure I should include that really. Okay, so ethyl propanoate. Esters used in perfumes and flavourings. Okay, so let me just add carboxylic acid, alcohol, ester, water. So much like our acid plus alkali goes to salt plus water, carboxylic acid plus alcohol goes to ester plus water. Okay, so one we should just be knowing straight away, nice and simple. Okay, so esters can also be made from acid anhydrides. So this is something we haven't come across before, and we're going to have a look at these. Okay, so this is an acid anhydride, and this is made, just let me change colour for that, this is made by taking 2 ethanoic acid molecules, so acid anhydrides there, let's straighten that up, so 2 ethanoic acid molecules, and it goes together to form that and water. So anhydride you've kind of got anhydrous a bit in there from the anhydride, meaning without water. So you've got your two acid molecules reacting and giving off water, okay? So this is ethanoic anhydride because they've each got two. And we can react this with, say, methanol. And that will make our ester and a carboxylic acid again. Okay? And this ester should be there ahead of me, is methyl ethanoate. Methyl ethanoate. Okay? So, one of the things we can do is we can split up esters. And this is in a process, so I'm going to put down breaking down esters. And we can do this through hydrolysis. Okay, and we're going to have a look at one of the types. So you can have acid hydrolysis, and you can also have base hydrolysis. And we're going to look at acid hydrolysis now. I'm going to leave base hydrolysis for the lesson. So bring your notes with a gap under base hydrolysis where we can fill in some ideas. Okay, so if we take an ester and let's choose this one. So that is going to be 1, 2, 3, 1, 2. That there is going to be propyl ethanoate. Okay, and if we add H2O to that, so hydrolysis has kind of got hydro, water in the name, and we do this in aqueous conditions with HCl, so we need our acid in there, and that will make this compound, these compounds here. Oh, sorry, that should be entirely red, that one. That will make these two, obviously propan 1-ol and ethanoic acid. And because it's in acid conditions, both of these groups have got their protons on. Okay, so we're in acidic conditions, so there's an excess of hydrogen ions floating around. So these have got their protons on. So when we come to base hydrolysis, and we've got OH minus ions floating around, we're going to expect something different. Okay, and that's what we're going to be looking at partly in the lesson. We'll cover all the other stuff previously, a bit of practice of that. But I want you to have a think about what you might expect if you had these two together in basic conditions. What might be different, if anything? Okay?